Oh, okay, welcome everyone. So I'm Alex Drlica-Wagner. I'm one of the members of the community engagement team. I'm a scientist at Fermilab and an assistant professor at University of Chicago. And I sort of got involved in all of this a few years back as a user like you, building up sort of tutorial notebooks that that the user community could use to learn about various aspects of the LSST data management pipelines. So that's just who I am, and today we're going to be going through one of those aspects of the pipelines, the data Butler. So before we get into that, we'll go through our usual announcements and breakout notes. So if you haven't already, now is a good time to log into the Rubin Science platform and to find a notebook. And the notebook that we're going to be running this week is the 04 Intro to Butler IPython notebook. Also, if we want to add any breakout topics, here are a few that we were sort of thinking of. Our usual Q&A question breakout room, any DP0 working groups that may be here today that want to have a breakout room, we are happy to set one up. And anyone who wants to talk about kickstarting new tutorials or analysis projects, or even working through some of the tutorials that we've set up or exist in on the internet elsewhere. Any other notes on this slide from anyone?
Also, I think you want attendees to open a new blank notebook to follow along with you.
They can, yeah, they can. I'm going to be doing, what I'm going to be trying to do is basically, I'm going to have two windows open. One is going to be the 04 Intro to the Butler notebook, and the other is going to be a blank notebook. And so I'm going to try and work through them sort of side by side. So you can read the documentation in the Butler notebook, and then I'll be typing and copying and pasting code into the blank notebook. But we can get all of that set up. Melissa, do you want to make these announcements?
I do, yeah. Three announcements for our DP0 delegates today. One of them has to do with the DP0 live session. So you're here in a delegate assembly. If this is your first time in an assembly, I just wanted to remind you that for the first hour, we'll have a formal presentation with Q&A throughout, so use the Zoom chat as needed. And then the second hour of today's assembly is going to be breakout discussions, like Alex just mentioned, where anyone can propose a topic for a breakout. People can join you, you can work together, work on your working groups, pretty much whatever you want. The second hour is for you to use as you needed, with Rubin staff here to help you with things. For this delegate assembly, we're going to be looking at the Butler. And then the little window here is showing you sort of the upcoming topics for the delegate assemblies. We have 3 more, so they're bi-weekly on Fridays. There'll be 3 more delegate assemblies with set topics and set presentations. Oh, thanks, Alex. Yeah. And then after that, we're going to still have bi-weekly delegate assemblies, but we haven't set topics for those yet because we wanted to provide space for delegates to present their own work and to present tutorials that you've done or science things you're doing with the DP0 data set, pretty much anything. So there will be a bunch of delegate assembly open slots. And if you're interested in presenting some of the work that you've been doing, that would be awesome. Just get in touch with me or anyone from the community engagement team, and we'll get you set up with a time slot to present your work and share it with the other delegates. Alex, can you zoom back out again? Yes, and then I also wanted to mention that in addition to these bi-weekly delegate assemblies, there are also more casual sessions the third Thursdays and the Stack Club sessions for co-working or getting help or whatever you need in terms of live sessions. The second announcement on the next slide is just a reminder of the DP0 New Friends program, where the science collaborations are looking to pair their long-term members with new to Rubin scientists and students. And you can visit the community forum topic at ls.st/DP0 CLO 5700. Someone from the CAT, please put the link in the chat for us. We can learn more about this program and sign up. So that's still ongoing. You've probably heard about it before. Third announcement is about preparing for LSST Kickstarter proposals. So this applies especially to anyone who's a member, even if you're a new member or who maybe you're about to join, the Transients and Variable Stars, the Stars Milky Way Local Volume, or the Science or the Solar System Science Collaborations. They've managed to put together a big funding opportunity where you can apply and get up to $20,000 if you're as an individual or a team, or up to $30,000 for partnerships to work on pretty much anything related to LSST preparation, and that includes your DP0 related work. So if you could use some funding for student training or your summer salary or for equipment and software or to run a seminar series, the scope of activities that can be supported by these grants is really large. The proposal deadline is coming up September 30th. And if you have any questions about this or what you might be able to propose for, please reach out and ask because the science collaborations want to make sure this money gets used immediately and in a really good way. So, and DP0 related work definitely counts for that. So there's the link, LSST SciPrep, github.io. I'll put that in the, I'll put that in the chat as well. And those are the announcements for today. Thanks, Alex.
Great, thanks, Melissa. So I'm gonna close these slides. And I will, I guess, start from scratch, or basically from scratch. So let me close this, All right, so I'm logged into the RSP on the interim data facility, so data.lsst.cloud. From here, I navigated to notebooks, tutorial notebooks, and O4 Intro to Butler notebook. So now what I'm going to do, and this is nice feature, is I'm going to move this notebook over here so I can see it on half of my screen, and hopefully everyone can see it there too. And then what I'm going to do is I'm going to open a new notebook, which is a blank notebook over here, which I can use as scratch space. So the hope is that by doing this, you can do the same. We can have the information over here on one side, and we can play around with executing the code or pieces of the code over in this blank notebook that we have over here. So hopefully people are able to set things up like this. You're also welcome to just run through this notebook in a single window, but I think it ends up being a little bit more fun to work through things like this. For context, maybe as just a brief introduction to why what we're doing and how it fits into the other notebooks that you've been seeing at the delegate assemblies. If you were around last week and you saw Jeff's great introduction to image display, you'll notice that there is one cell at the beginning of this notebook where Jeff got his data. And so we didn't dive into this in much detail where the DP0.1 data was coming from, but that's basically the entire point of the tutorial today, is to understand this cell block here and some of the other capabilities that the Butler, this tool that we're using to access and investigate the data sets, some of the other cool things that we can do with this object. Okay. So to get started, we're just going to do some generic imports. And so this cell block here consists of a set of generic Python imports. So you can see this run here. And then we're going to import a number of tools from the LSST science pipelines. In particular, oops, let's do this. In particular, we're importing the Butler. This is a module that contains the Butler itself. We're importing a module that gives us access to a bunch of display tools. we're importing some geometry tools and some coordinate tools. So these will help us with some of our geometry and coordinate dependent queries that we'll make for data sets later on. And then we're setting the display backend to matplotlib. So we should be able to execute that, and that'll import those tools there. So the first thing that we're going to try to do is create an instance of the Butler. So the Butler is this object that helps abstract away the need for you to know any specific paths to data sets. And so it combines together some databasing as well as an understanding of file structures and hierarchies, so that it allows you to both investigate what data sets exist and get access to those data products in a programmatic and queryable and scriptable way. And so the Butler is used as sort of a core piece of the science pipelines, because it basically allows you to track and access input data and data products that come out of the processing of the science pipelines. And so for the nomenclature that we use is that the Butler is accessing data sets within a data repository. Those data repositories contain something that is a database component, which basically indexes the information that's present in the repository, and a file-like storage component, which doesn't necessarily need to be a local file system. On some instances it is, but in our case, we're actually pointing to S3 buckets, which are non-local cloud storage components. So to start out, we can create an instance of the Butler pointing at a specific repository. And so this is a non-local path. So it's telling the Butler to look for the data sets in this S3 bucket. And so this will execute, and it'll give us an instance of the Butler. So here's our Butler, right? It's a DAF Butler. If we want to learn a little bit more about it, we can type help Butler, and we can see all of the call that was made to create the Butler. So what we passed it was just this this directory type object that was enough for the Butler to find the configuration file that it needed to instantiate itself. But there are a number of other things that we can pass in when we create the Butler. In particular, we're going to explore the collections that we can pass in. The collections are sort of subsets of the data sets that the Butler knows about. There are also a number of different methods that we can call on our Butler instance to check if data sets exist, as well as to get various different data sets. And so we'll be exploring that in the notebook as well. Okay, so I'll get rid of this. And the first thing that I'm going to do, so we created our Butler without any specific collection. Because at this point, all that you can imagine as we've been pointed to is this one S3 bucket, and we don't actually know what data sets exist in there yet. So if we want to find out what data sets exist, we can create a registry, or we can access the Butler registry. So this is the database-like component of the Butler. And then we can ask the registry, what collections do you know about? And so this is printing a list of collections. So these are sort of subsets of the data that the Butler knows about. And you can notice that they're broken down. So 2.2i, this path prefix is historical. It's coming from a specific run of the LSST desk DC2 data that goes into creating DP0.1, the DP0.1 data set. And so that's where the 2.2i is coming from. There are also a set of reference catalogs. There's a set of sky maps, which actually give you geometric representations of the data set. And then you can see that there is also a place for user data. So this is a specific user who has performed some runs of the science pipelines where the outputs of those runs have been stored as collections of their own. So the other items here are calib, which refers to calibration products, the raw data, and some of the reruns. So these are the processing runs of the raw data that went into DP0, which is the desk TC2 data. So we can look at these collections, and what we are going to be interested in is process data. So we want something under the runs directory here. And in fact, we can point to this high level collection, and it actually has it contains a set of sub collections in it. So we can just choose this collection and instantiate a version of the, so here we're querying what this collection contains. We can see that this collection actually has a set of sub collections which point to the other collections here. So a set of calibrations that were used for the processing, the raws that were used for the processing, as well as various different processed data sets. So this looks pretty good for us. So we're going to create a new version of the Butler that points at this specific collection here. Okay, so now we have a Butler. It's an instance that now knows about the collection that we specified up here. 2.2i runs DP0.1. Okay, so now that we have a collection of data products, what we may be interested in is what kinds of actual data types exist within this collection. So if you think about your just a generic astronomical survey, you have the exposures that you actually took of the sky in both their raw and their processed forms. So we refer to those as visits in LSST land. The processed exposures are referred to as CalX, the calibrated exposures. And then in addition, you can take these processed image products and you can co-add them together to get deeper co-added images, which are also remapped into different regions on the sky so that you can add together multiple images and look at various regions. And these are the co-add data products. In addition, there are catalogs that come out of the processing. Those are generally referred to by this source, SRC, in their name. So there are sources that are extracted both from the single epoch or the single visit processings, so from the CalX, and sources that are coming out of the deep coad. So the deep coad for source catalog. So these are catalogs of sources coming from the deep coad. This is giving us a list of the data set types that the Butler registry knows about. Here are some descriptions that I just said in words of various types of data set types that you may be interested in accessing. We're generally interested in either the CalX, which are the process visit images, or the deep coads, which are stacks of multiple CalX. The other thing that we're going to want to know, in addition to the type of data that we're interested in, will be the actual references to specific data products. So if we're interested in CalX, we may be interested in the CalX from a specific visit and detector. So the processed image from a single CCD associated with a single visit of the LSST camera. In this case, it's all simulated data from desk DC2, but the idea is the same. I see that the chat has been going, so I'm going to take a minute to pause here and look at the chat, and also take a time for anyone who has questions to ask. Okay, great. Any other questions while I'm paused here? About anything that I've been talking about?
I think Natasha's question was a really good one, so I'll just amplify it so everybody hears that she was wondering why you reinstantiated the Butler pointed to a particular collection since we had already instantiated the Butler before. And Simon already answered in the chat, but that I thought it was a good question to highlight that you don't actually have to do that. You can specify the collection when you instantiate the Butler so that then you won't have to do it every time you do any Butler calls later. But you don't have to do it there. You could just include that collections equals collection line in every other butler.get or butler.whatever call later on.
Yeah, great point. And for the most part, once you know that this is the main collection that you're interested in for your DP0.1 investigations, most people will never instantiate this raw Butler without specifying the collection. So almost every notebook that I write starts with this line where I've instantiated the Butler with the specific collection that I know I'm going to want to work on. However, if you don't know what exists in the to start with, you may want to just instantiate the Butler and be able to look at the collections that exist in order to choose one. Yeah, that's a great question. Okay, so
the question from Leanne.
Thanks. Just looking for the unmute button. Yeah, that's a great question and answer. Thanks, Alex and Jeff. But I just have another question on that. Is there no way to then update the instance of the Butler by specifying the collection and making that a permanent feature of the Butler instance after you've instantiated it? Are there any two options? Like you instantiate a Butler without a collection, and then every other call has to specify the collection. You can't just take Butler dot specify collection and then give it a collection, and then your Butler is now updated for all time. Is there no method call like that?
I asked the same thing to Jim Bosch if he wants, or someone else maybe wants to take it. Sorry.
Yeah,
no, not at the moment. Oh, okay, go on, Jim.
Yeah, there isn't. I think mostly because there's a lot of setup stuff that happens when you specify the collection, and it's easier just to do it construction. There's really no drawback to making a new Butler. And if we were to allow you to set it, it would be equivalent under the hood to making a new Butler.
Okay.
And you should be able to instantiate a Butler from a Butler, I think, where it might work if you do that.
That's an interesting test. I'll try it in the breakout. I'll try it after this, after I finish listening to Alex. All right, thanks.
Great. Okay, so I think we are now at the stage where we are interested in what data set types we can get at. So, okay, we did this before. We talked about coads and source catalogs. And so now let's try and access a specific calibrated exposure from, or we'll see what calibrated exposures exist belonging to our collection and some metadata information about them. So if, for example, you're interested in just seeing, sort of a small sample of calibrated exposures. So these are single CCD detector images that have been passed through the instrument signature removal and characterization steps that go into the science pipelines. And we just want to take a look at sort of what metadata can be associated with these calibrated exposures. So these calibrated exposures have a specific band, the R band. So this is the filter that was placed in front of the simulated filter that was placed in front of the simulated LSST cam for observing the sky. They have a detector number. So this refers to which CCD and LSST cam the image corresponds to. And they have a visit number. And so this is the exposure, basically the exposure that was being taken of the sky.
Sorry, Alex, just to be absolutely clear,
Yes.
the visit is not an exposure. The
Right.
visit, because in LSST CAM, an exposure is a single exposure of the instrument, and a visit can be multiple exposures.
Right, right. So the current observing plan is to take 2 snaps of each region of the sky. And so the point that Tim was making is really important one, is that there are these 2 individual exposures that go into a single visit. Is that what you're getting at?
Yes, so you will see that some data IDs have exposure as a dimension and not visit. And then later on, as part of the pipeline processing, there is a point at which where exposures are combined and they become a visit, and then visit is what's used downstream in all the processing. But you have to, in order to avoid confusion, you have to conceptually think of visit as not necessarily being identical to exposure. In the case of these DC2 simulated data, visit and exposure are the same thing. So because there's a one-to-one mapping and the IDs are identical, but for LSST CAM, that might not be the case.
Thank you. Okay, so now once we've identified, say, a few of these calibrated exposures that exist, a natural thing to do would be to grab one of them and plot it. You may think that the first thing you would do would just be to ask for a file path, and then grab the exposure and open it or grab the image and open it in DS9. In the case of the IDF, these data products are actually living in an S3 bucket, which isn't on the local file system. But the Butler is able to tell you the effective URI, so the uniform resource identifier, basically the information that you need to access that chunk of data. And so what we can do is we can loop through and find these URIs for these FITS files. In reality, you don't actually need this path-like string. You can ask the Butler directly to get this data product for you, and it will return to you an object which you can then act on to plot or to analyze or to work with as you see fit. Okay, let's see if that runs. So what we did above while this is running was just ask for sort of a unspecified set of calibrated exposure CalExps, so process visit images. And so we didn't, you can see we got a mix of bands here. We got some G-band images, some R-band images, a variety of visit numbers, a variety of detector numbers. We may be specifically interested in data products that come from a specific band or a specific set of visit numbers. And so we can also query for data sets that are matching a set of constraints. And so here, what we do is it's essentially the same operation that we performed up above, but we're querying for visits that have a visit number that's greater than 700,000 and that were taken in the G band. And so if you are familiar with SQL queries, so SQL is a query language for relational databases, then this may look familiar, this construction may look familiar. So this where clause can actually take a wide range of different information in it. You can specify specific visit numbers, specific detector numbers. The band information can go into the where clause here. But this is a way to sub-select a data set from the overall set of data that's known about by the registry that is assigned to the Butler. So now you can see that the set of references that are returned have metadata that's all G-band and is all visits greater than 700,000. We can also specify various different dimensions to the query that we're asking for. So we can ask for exposures, visits, and detector information that satisfies some set of conditions. So here we're asking for a specific visit and a specific detector. And we're getting metadata associated with the exposure, the visit, and the detector at the same time. And so if we run this, you can see that we're getting exposure information, which has information like the exposure time, the filter, the visit ID, but also some RA and DEC information of the exposure and the time at which the exposure was taken. The visit has some additional information assigned to it. So some geometric information about the sort of like a polygon, the area on the sky that it's subtending, as well as timestamp information. And then the detector is information about the specific CCD in LSST PAM that this data product is coming from. Okay, and so if we have a specific piece of data that we're interested in grabbing, we can access it actually by the data ID itself. So we can also, and we'll show this a little bit later on, but this is giving us all the information that we need to be able to ask the Butler to return to us a specific calibrated exposure. There are other more complex queries that can be done. We can query on time spans and on regions of interest. And so this is a really cool thing if you're interested not just in getting calibrated exposures that are in a specific band, but actually getting visits that were taken in a specific time span or visits in a specific region, then we can do that as well. And so there's a good example here, which I think I can just skip ahead to, where what we're doing is, I think I'll need to get the record first. Okay. So this is getting a record associated with a specific visit. That record has a time span and a region object. So a time span is a temporal span and the region is a spatial span. And then what we can do is we can grab other visits, for example, or CalExps in this case, where the time span during which the CalEx was taken overlaps with the time span from this visit. So this should work. And what we've actually done is we've added a minute on either side here. So we're not just getting the specific visit that the records above belong to, but visits that were taken, or CalExps from detector 46 that were taken in visits that are within 1 minute of the time that our previous record, our previous CalEx from this visit number were taken. And so you can see we're getting detectors that are coming from visits that are adjacent in visit number. And that's constrained by the ±1 minute selection. There are also ways to do spatial queries. So, you know, in this case, we're effectively querying for visits that were taken at similar times to our visit of interest. We can also query for visits that are taken in roughly the same region of the sky as our visit of interest. And to do this, we use something called the hierarchical triangular mesh, which is a convenient pixelization of the sky. So this allows us to search within a subregion of the sky quickly for visits that were taken within that subregion. So we can execute these blocks as well. So what we're doing is we're finding the ID of the triangle that is specified by this the location of our visit of interest. But I mean, this could be any RA in depth that you choose within the DP0.1, the DC2 footprint. And we're looking for this ID is a triangle that covers, that has a scale of about 270 arc seconds. And once we have this, this triangular mesh ID, we can query for calyx that belong within this, this area. And I think this will only return one visit in this case, but we can change the triangular mesh scale, so we can select larger or smaller regions of the sky, and that can allow us to get visits over larger or smaller patches. Okay, so these are sort of some of the cool ways that you can use the Butler to query data according to different conditions that you may have. So I'll pause here for a bit for comments and questions, and I'll try and read the chat while I do that. So there's a question about what temporal and spatial queries can be done in the portal. So if anyone has more portal experience than I do, want to comment on this, I think, yeah, I'll pause and let anyone want to comment on that.
Presumably this is all going to be handled by the VO image services. So you can ask what data do I have in region X, and it'll happen. But I mean, it's whatever the VO will support.
Yeah, to add on that a little bit, the portal doesn't currently use the Butler behind the scenes, so it doesn't do things the same way. The image services that come along may use the Butler, but it will not expose the same API. It will be the VO version of how to select regions. So, but those services are still under development and don't exist at the moment.
Okay, so the next part of this notebook is going to be actually grabbing a data product and visualizing it. So this follows on the notebook that Jeff shared last week, but goes into a little bit more detail about grabbing various different kinds of data products. So we're going to start off, we're going to grab a calyx. So these are processed, a single CCD from a processed visit of LSST CAM. This dictionary that we're creating, and we're naming data ID, is giving the specifications that we need to uniquely identify one calyx. So it has a visit number, it has a detector number, so that's the CCD, and it has a band. You don't need to specify the band here because the visit and the detector should be enough to uniquely identify the data product that you want. So let's try this. You'll notice that this seems to be popping out of thin air here right now, but what we just did, all of the work that we did for various different querying techniques can be used to get this information. So you can notice that we were able to get data IDs up here that tell us the visit and detector number. And so, for example, if you're interested in querying for detectors in a specific region of the sky, you would first run sort of the spatial querying code, which would result in a set of data set references from which you can get the data ID. And then you would be able to pass those data IDs you can pass the data set references itself to the Butler to get the data products. So we're using this butler.get method to actually get the data products. So let's try this. And so this will return to us this calyx object. If we want, we can learn a bit more about it. Right? It's got a lot of different methods that allow you to get images, get mask data, get metadata, get the WCS, get the PSF. You can get a lot of different metadata from this calyx. So for example, let's see. You can see the image itself, and you can actually get the image itself as an NumPy array if you want. So you can play with the calyx a lot. They also have a mask plane. You can get that as an array. Right, so this is the mask flags. And as we saw last week, we can also use the built-in AFW display methods for plotting the calyx. So this should go ahead and give us a calyx. Yeah. And so, so if we wanted, we could plot not the calyx, but just the image. And so you can see now the mask plane has disappeared. Or I think we can plot the mask. I'm not sure exactly what this will do. Yeah, this will complain because we're trying to scale a unsigned integer, I bet. You can see here in the image that's being displayed, in the background, we have the actual image, and then we have mask bits that are being overlaid on top. So what if we also want to get the catalog objects that are associated or were derived from this calibrated exposure? Well, we can use the same data ID that we used to get the calyx data set type to get the sources that are associated with it. So here we can get the sources, and we can learn a bit more about the sources. So the sources are a source catalog. We can get them as an AstroPy table. We can also have different views of the sources, and we'll look at that a little bit more in detail. One thing that is often necessary is to sort of remap this in memory. And the easiest way to do that is with a source copy. And this is, you shouldn't have to worry too much about that. But we now have sources that we can plot on top of our image. So let's see how that goes. And so here, this is the calyx that we were showing above, now with the sources plotted on top of them. And you can see it works. Great. Okay, so I'll pause here for questions about getting the image or the source catalog associated with it. Yeah, good question about, right, so the LSST camera has a lot of detectors. There's 189 science sensors in it, as Simon was saying. So the full image is, or the full output of a single exposure is a rather large data set. Each one of these is roughly 4K by 4K. So that's, 16 million pixels in one calibrated exposure. And so you can grab multiple calyx at a time, but you start running, especially if you're trying to plot multiple ones, you can run into memory issues. Any other questions about grabbing calyx or source catalogs? Okay. All right. So the next thing we're going to do is talk about how you can select cutouts, so small subregions of an image, and actually use the Butler to get those cutouts directly. So you might imagine that what you would need, or what you may be familiar with from other astronomical data sets, is grabbing an entire image and then sub-selecting a region of that image. And in fact, you can do that. So I have my calyx here, right? And I can get the image array as a NumPy array here. And I can, sub-select in some set of pixels, right? And I can even, right, so I can make a little image of a subregion. I can do even smaller, right, if I want. And so this is what you may be used to doing in the past. But this is not very efficient because, as it was mentioned, you grab this 100 megabyte file in order to make a cutout that's only 50 pixels on a side. And so the Butler can actually allow you to get this cutout directly, rather than having to grab the entire calyx and then making a cutout yourself. And so what we've done is defined a little utility function here that takes the Butler, an RA and a deck of interest to you for your cutout, a band of interest, and then a data set type. So in this case, we're going to be querying the deep coad images. So these are stacks of multiple calibrated exposures that have been stacked together. And we'll specify the size of the cutout that we would like to generate. So I'm going to copy this over, just walking through this a little bit. What it does is it takes the RA and deck that you've specified in units of degrees and creates a geometry object, a sphere point geometric object from that. And then it specifies the size of the cutout that you would want. So the length, so that's in this case, a 51 by 51 pixel cutout. It then grabs the sky map, which allows you, gives you the utility you need to look up what tract and patch. So these are the organizations of the coads. They're broken up into smaller sections of the sky that you can then grab individually. If you know the RA and deck of that tract, you can grab a tract and a patch. You can specify the XY point of the RA deck that you specified within that tract. And then you can define a bounding box object that has the size of the cutout you want to generate. And you can then get the patch info from the tract itself. This allows you to specify a data ID. In this case, So for the calyx, we needed to specify a visit number and a detector. Now we need, for the coad, we need to specify a track, a patch, and a band for the coad. And in addition, we're giving it a bounding box object. So it doesn't grab the entire patch or the track, but just the bounding box of it. And so then all of the hard work is done in the butler.get function, where we're now giving it the coad, the deep coad data set type. We're giving it the bounding box that we want to subselect, and we're giving it the data ID, the specification of the data set that we want to grab this bounding box from. So I'll copy this over. Into my Scratch notebook. And then I'll use it to try and get a cutout from DCP. And then again, I can display that cutout using the usual AFW display. Okay, cool. So now we have an image of a cutout. So we can also grab catalog data, and we can grab catalog data that is associated with this deep coad force source catalog. The first thing we can do is we can see what schema, so this is sort of the table structure that is associated with this force source catalog. The force source catalog has some number of columns. In this case, it's 508 sort of measured quantities associated with each object in the force source catalog. We can also query for specific column names. So in this case, we're doing a query for columns that contain the word PSF in them, with the understanding that these are some some measurements related to the PSF, and we can then extract, various properties from the schema. And so in this case, what we're showing is a way to get documentation on the columns in the schema. Okay, so what if we want to grab catalogs associated with the tracked and patch that we were identifying above in our for our cutout. So to do this, we could define another function to get sort of catalogs based on an RA and DEC, but this is essentially the same pattern that we had above when we were generating the cutout image. And so what we do again is we specify an RA and DEC, and we use the sky map to get information about the tracked and patch that overlap, that contain that RA and DEC. We then build the coad ID. In this case, we've specified that we want the IBAN tracked and patch, and then we get the force source catalog associated with that track and patch. We can convert it to various useful formats, which allow us to print it nicely. So this is printing it as a pandas data frame. We can also print the coad source as, and this is printing it as an estrified table. One thing to note is that the RA and DECs are actually stored in radians internally. So that's something to keep a lookout for. So if we want to plot the distribution of sources on the sky from the track patch combination that we queried, we can do that with matplotlib by taking the RA coordinate and DEC coordinate from our source catalog converting it to degrees and plotting those locations, those RA indexes as a scatter plot on the sky. And then I've just overplotted with the triangle the RA index that we actually queried for. So this was the position of our cutout. And so you can see indeed it's contained within this patch. Okay, and so this sort of takes us to the end of the Butler tutorial for querying data products. So just to summarize, we went through some ways to query for different temporal and spatial requirements on data products. We grabbed a calibrated exposure for a single detector and plotted it. We then defined a function to grab cutouts from deep co-added images in a specific region of the sky. And then also we're able to grab the associated source catalogs that were associated with that deep co-add. And so with these tools, you can play a lot of games. Like, for example, maybe a good thing for a breakout room would be to try and overplot the sources on our cutout image, for example. That could be interesting. We could also look at the properties of the sources that we've grabbed, make color plots, color magnitude diagrams, look at the distribution of sizes, play around with various different catalog properties from that. So I think that takes us to the end of the tutorial notebook. I'm happy to take questions, or we could come up with brainstorming of different topics for breakout.